Hi everyone, welcome to another video in the CBM Flux Studio series. The subject of today's video is going to be weak bits. Specifically, we will have a look at what behavior they exhibit and how to create them, possibly speculate on how they were found back in the day, and perhaps how they were written back in the day. Let's just focus on Zaxxon for the time being. If we open the G64 I created from nib file, which was shared by Sebastian as a reply to one of my blog posts, you can see that on track 1 sector 0, this is the CBM header for it, and this is the data part. There are areas here where things don't look quite right. For a standard Commodore disk, there are 3 0 bits in a row in a number of areas here, and those are not valid CBM GCR values. However, they are supposed not to be, because this is what the protection is requiring in this area. Now, unfortunately, this G64 will not work as it is, and the reason is that even 3 bits in a row will not cause weak bits when the disk drive is reading this G64 image. I will not work on the image directly. What I will do is we'll open a different one that has been created from a D64. Now, believe it or not, we had to do this, and this was discovered by FlavioWeb, because working with the G64, even when we fix the issue with weak bits, the game doesn't load. But if we convert to the D64, convert back to G64, fix the weak bits area, then the file works as expected. It's one of those things we don't understand yet why, but we are on the case. Now, if I'm trying to load this file in Vice, let's unpause emulation and load it. You see, it gets on track 1, and then what happens is that it's pretty much trapped in a loop. On device 8, which is the one looking for the sentinels on track 1, and then looking for changes in the values read in the weak bits area. Now, unfortunately, the way the G64 is causing a deterministic read at emulation time, and it would cause deterministic reads even if these G64s were written back to disk. Unfortunately, it doesn't get any better even with a G64 created by DTC, and I can show you what that one looks like in the area of the weak bits. Unfortunately, there isn't enough of them. Even if there are 5, there aren't enough of them. Another thing that this G64 helps us understand is that the data part of this protected sector has been rewritten, and that's because of this pattern you see here, this disruption. You know, this one doesn't show the same problem because it wasn't rewritten. So this was formatted, and this was, you know, pretty much a continuous stream. This one, there are hints here that this was rewritten. So the tool that was used to create weak bits has rewritten the data part, which is something we will do ourselves in a minute. So let's go back to the G64 we were working with. As I've shown in my code, in a disassembly of the protection, the drive code is really looking for some sentinel values in the data part of this sector, and the first sentinel is looking for is D5, this one, just after the GCR value 55 in X for the block ID for CBM data. So this one needs to be read properly. This will be no problem because the framing is okay at this point. Then what he wants to read is random values here, 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 and then he wants to be able to read again AA and D4 after this point. Now those values are not here. You can't see them working here, so they need to be reinserted in this image. The way I'm gonna do it is by using a tool I wrote, and so let's have a look at what that tool looks like. Pause emulation. And now what we can do is to attach a disk image to drive 8. Can use the copy for these purposes, and you can see that the code went to track 1 and did something. Let's see what exactly it did. Just detach the disk image first, and then what I can do is to go here and have a look at what happened here. Now off the back you can see that we have the same sort of artifacts here that suggests that the CBM data was rewritten by a process. So let's have a look what we have in the data block. Just for convenience, it makes sense for me to move this stream just slightly by 1 bit, so we can read familiar values here for the block ID. What comes next, which is D5, one of the sentinels. Then there is AA, which is fine. Then here we will have random values read all the time by the drive, and after them we have another sentinel, AA in X, and then D4 in X. This is exactly what's required for the protection to pass on track 1. And without further ado, let's see if that works. So I detached that disk, but what I can do is put it back in, and let's see what happens once the drive goes to track 1. So it's on track 1 now. The protection on weak bits passed, and now it's loading the main file with the custom loader. It'll be done by the time it gets on track 12, so bear with me. So there you go, the game loaded. can't guarantee that everything is as it should be because we converted to the D64 first, but at least we know that we can fix the issues around the areas that produce weak bits at read time. And I'll just show that you know, at least there is something that is working. So the game starts. Again, we don't know whether or not it crashes later on, but as you can see, the game has loaded. So yeah, that fixes the issue with weak bits. And essentially, I believe that a tool like this was used back in the day to just blank out these areas, which would cause a loss of sync at read time, and then it would also cause random bits to be read in this area, but the framing might be lost. You know, there's a few different possibilities, but usually the framing is 1 bit off when these areas are with a lots of zeros are read by the disk drive. So this AA here and this D4 value might be off by 1 bit, again due to the loss of framing. But eventually, if you read it enough times, what happens is that you will hit AA and D4, so the framing will be correct, and that's exactly what the protection counts on. That's why it goes on and reads over and over this sector, because it knows that eventually it will get the framing right. And that's one way to, you know, essentially check in a robust way something that is not robust in nature, which is, you know, mind-blowing. Makes you wonder, you know, how much field testing they did before they were confident to ship this one as a copy protection, you know, as a commercial product. You know, knowing that there would be liability in case users wouldn't be able to load their original games. But yeah, they got it right. They probably found about this while experimenting with 3 or more 0 bits in a row, you know, breaking the GCR Commodore GCR rules. And they probably used a very similar tool as the one I'm going to show right now. So the tool is essentially a little bit of a basic boot, and I think at the last count these were around 50 lines of assembly code, and this is inspired to the book Inside Commodore DOS. I'll put down the pages I was getting inspiration from, but essentially what the basic boot does is use direct access to the drive to load track 1 sector 0 into the drive's RAM in one of the buffers, buffer number 1. It then converts via the drive code, converts the contents of the buffer back to GCR, and then this is where things get interesting. This is where we destroy essentially 3 GCR values. We set them all to 0, but then what we also do, because we are not sure about whether the current read was okay or not, the framing was okay or not in a clone, in a copy, we actually reintroduce all the sentinels that the original protection checker is checking for. So this will make the essentially will make the clone work and pass the protection check. Everything else is boilerplate, which means it's taken directly from the Inside Commodore DOS code that creates errors on the disk. So we find the header for track 1 sector 0 wait out for the gap to be over. We enable write at the sync for the data block. Then we write all the GCR codes to disk, and there's 325 of them in total, which is the GCR equivalent of 260. That's the payload for the CBM data. And in the end, we disable write. We do a little bit of cleanup, and we report on success. That's pretty much all that's required for this, for creating a disk that will produce random bits in this area once it's read back, and that's what's referred to as weak bits. Now, considering that this was pretty much all of this was very well known, and again, all of this is from the inside Commodore DOS. So given that this was all well known, I'm surprised there weren't tools like mine around. Maybe there were, or maybe people would just use things like Maverick for editing the low-level GCR values directly, which Maverick's GCR editor lets you do. So that's a possibility on how things were done. But even if these sequences were written by Maverick, I think Maverick would have to start writing from a sync. So wait out the gap and write a new sync, which means this sort of artifacts would be shown. And yeah, that's that pretty much sums it all. Yeah, if you have got questions, ideas, opinions, feel free to leave a comment below the video. Otherwise, I hope you enjoyed it. Thanks for watching, and see you in the next one.